We're now finally in a position to study what's called the fundamental theorem of calculus. Now this, as its name implies, is probably the most important theorem in the study of calculus, hence we use the term fundamental. And it's really quite an amazing result. And it makes this statement. We start out with little f being a continuous function on a closed interval ab, and we assume that capital F is an antiderivative for our function little f on the closed interval ab. Then the definite integral of little f from a to b is actually equal to the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. And this is the notation that we use to denote that. So this simply means evaluate f at b and then subtract from it the value of f at a. So this simply means this right here. It's really an amazing result when you think about it. Let's take a look at a graphic here. Go back to one of our graphics that we've seen before. So here, if you recall how we evaluated the definite integral previously, what we did before is we used a limiting process via a right or left rectangular approximation method, or some rectangular approximation method. For example, this quantity right here, if you recall, this is simply a summation of areas of rectangles, with this piece right here, f of ci times delta x, representing the area of one small rectangle. For example, if you look at this graphic down here, the ci might be right there. F of ci would be the height of this rectangle. It would be this distance here. And then the delta x would be the width. So when you evaluate f of ci times delta x, that simply represents the area of one of these rectangles. And then the summation means you add all of these areas up, and then you take the limit as n goes to infinity, and that will give you the value of your definite integral. And you interpret that as being the sum of the signed area between the graph of the function and the x-axis. For example, graphically here, you notice if we let n go to infinity, you notice how the areas of the rectangles are filling in the area bounded between the graph of the function and the x-axis. So for this particular picture here, if we think of this as being area A1 and this as being area A2, the definite integral is the sum of the signed areas. So in this case, it would actually be A1 minus A2. Remember, when the function dips below the x-axis, the definite integral interprets the area to be negative, or in this case it would interpret the integral from c to b of f of x dx as being a negative quantity, the absolute value of that negative quantity being the area A2. So what the fundamental theorem tells us is that instead of going through this whole process here to evaluate this is a rather arduous process to evaluate. Remember, we did it with right rectangular approximation methods. Instead of doing that, we can simply state that this is equal to the antiderivative of f at b minus the antiderivative of f at a. So all we have to do is find an antiderivative for little f. Now, let's go back to the fundamental theorem. So let's take a look at an example here. Now, first of all, note we have the proof here, which we will look at, but we'll do that in a separate video. The proof is actually very elegant and fairly easy to follow. So we'll do that in another video. Let's take a look at an example showing you how to use the fundamental theorem. So for this example, we want to evaluate the definite integral of the square root of x from 1 to 4 and interpret our answer. So by the fundamental theorem, what we have to do is we have to find an antiderivative for the square root of x. Well, the indefinite integral of the square root of x is just going to be x to the 3/2 power times 2/3 plus c. So that's the indefinite integral. So to evaluate the definite integral by the fundamental theorem of calculus, what we're going to do is we're going to consider just this piece as being our capital F of x. In other words, we're just going to let the c be 0 now. We only need one antiderivative when we use the fundamental theorem of calculus. So we'll just let the c be 0. So then what we have is the definite integral from 1 to 4 is going to be the function in the box evaluated from 1 to 4. So it's just going to be this. And that's going to equal and let's see, 4 to the 3/2 power, that's going to be the square root of 4 cubed, and so that will be 8. You could check that out on the calculator if you'd like. And 1 to the 3/2 power is just 1. And we end up with 16/3 minus 2/3, or 14/3. And so what this number represents, it's the definite integral of the square root of x from 1 to 4. So here's the graph of the square root of x. So what the 14/3 represents is this area, the area of the shaded region that we have here. So this area is 14/3. So that's exactly what the fundamental theorem does for us. Now notice one other thing up here. When I said just let the arbitrary constant equal 0, if you had had some number other than 0 for the arbitrary constant in here, notice that when you do the subtraction process here, the constants would have just canceled with each other anyway. So when we apply when we find an antiderivative for our integrand here, we usually just let the constant be 0 when we're evaluating a definite integral. Let's take a look at another example. So here we want to find the area bounded by the graph of y equals 2x squared minus 3x plus 4 and the x-axis for x between 0 and 2. And right here is what we want to find. So this is our function right here. That's our 2x squared minus 3x plus 4. And we want to find the area of this shaded region in here. Well, all we have to do is evaluate this. So now what we need to do is find an antiderivative for this function, and, well, just evaluating each piece individually and adding or subtracting. Let's see, the antiderivative of 2x squared is going to be 2/3 x cubed. Antiderivative of 3x is going to be 3/2 x squared. And antiderivative of 4 is just 4x. And we don't worry about the arbitrary constant because we're evaluating a definite integral. Now we need to evaluate this from 0 to 2, and we put 2 in for x, 0 in for x, and subtract those two numbers. And so what we're going to get is And just note, if we put 0 in for each x here, we're just going to get back 0. So now this is going to equal and then just evaluating this quantity, we're going to get 22/3, and that value is the area of the shaded region that we have here. So this area is 22/3. And so see how easy that was to evaluate. That's what's amazing about the fundamental theorem, is that it relates the area bounded by the graph of the function in the x-axis to the antiderivative of the function. It's really an amazing result. Let's take a look at another example. So here we want to evaluate the integral from -2 to 3 of x squared minus x minus 2 dx and interpret the result. So this is a definite integral. So we'll do part A first, and then we'll take a look at part B, where we want to find the total area of the region bounded by the graph of that function and the x-axis for x between -2 and 3. So first of all, part A, that's fairly easy. So we just have to find an antiderivative for this function. That's fairly easy. That's just going to be and then we evaluate that from -2 to 3, meaning that we put 3 in and -2 in and subtract the two values. All right, and now evaluating this quantity, we're going to get -5/6. And once again, the easiest way to evaluate this is to plug this function into one of your Y1 or Y2 registers of a graphing calculator like a TI-83 or 89 and evaluate Y1 of 3 minus Y1 of -2. That's the easiest way to evaluate this. Now let's take a look graphically at what this quantity -5/6 represents. Notice we have a negative number here. So let's see what's happening with our graph. Well, we have the graph down here. So this answer was -5/6. Let's just put that off to the side here. So what this quantity represents, looking at it graphically down here, notice we have -2 right here on the x-axis, up to 3. This is the graph of x squared minus x minus 2. And notice that we have these three regions where the graph is above the x-axis, below, and then above again. So what this quantity represents is going to represent area A1 minus area A2 plus area A3. So it's equaling A1 minus A2 plus A3. And so since it does look like the red region is a little larger than the sum of A1 and A3, that's why we have a negative quantity for the definite integral. Now let's take a look at part B. Now for part B, we want to find the total area of the region bounded by the graph of this function and the x-axis for x between -2 and 3. So if we, moving down to the picture here again, our graph, for part B, what we actually want to find is A1 plus A2 plus A3. So that's what the answer to part B is going to be. Keep in mind the answer to part A gave us A1 minus A2 plus A3. So what we're going to have to do with this problem is we're going to have to find where the graph dips below the x-axis and then break the integral, the definite integral, into three separate parts. We're going to evaluate the definite integral from -2 to this point. Looks like it's about -1. Now when we evaluate that, that'll give us a1 and it will be positive. Then we'll evaluate the definite integral from this point to this point, which looks like it's about 2, and that will give us a negative number. So we will take the negative of that number, which will make it positive, or just take its absolute value. And then we'll evaluate the definite integral from this point to 3, and that will be a positive number because the graph is above the x-axis in that region. So that's how we're going to do this problem. So we need to find where our function dips below the x-axis and break our integral up into three separate pieces according to this picture. So let's do that. So we need to find where x squared minus x minus 2 is equal to 0 first. Where does it cross the x-axis? Well, this function factors as and so we see that the solutions to this are -1 and 2, as we suspected from the graph that we saw below. Now let's just double check where this graph is positive and negative. Pretend we didn't see that graph down there. Normally you're not going to be given the graph for these problems. So what we can do is just do a quick sign pattern test. And so this will be for the sign of this function. So if we take a number like -2 and plug it into our function here, you see we'll get back a negative times a negative number, so our function is positive here. And then if we take a test point like 0, put it in here, we'll get negative times positive, that will be negative. And then from 2 to infinity, just picking a test value like 3, we see that our function will be positive. So then, the total area is going to be this. It's going to be the definite integral from -2 to -1, and then minus the definite integral from -1 to 2, you see this quantity here is going to be negative because the function is below the x-axis from -1 to 2, and by going minus a negative number, that will make it positive. Or you could go plus and take the absolute value of this number, of course. You could do that as well. And then finally plus the definite integral from 2 to 3 of like that. And then of course this quantity, evaluating each one of these, we get, now remember the antiderivative of x squared minus x minus 2, that's going to be, and for our first term here we have to evaluate that from -2 to -1, and then we have the other two terms. And now to save time, I'll just tell you, I'll evaluate each one of these and tell you what they are. You can certainly evaluate these on your calculator. Remember, for the first one here, you would put -1 in for x, get that number back, and then put -2 in for x, and then subtract that number from the first one. And you do that for each one of these. So what you're going to get then is, for the first term here, you're going to get 11/6, so this one is 11/6. The second term here is going to be minus, this is -9/2. And then finally plus the third term here, that is also 11/6. So what we get then is 11/6 plus 9 halves plus 11 sixths, and that evaluates out to 49 over 6, which is positive, which is good. We should get back a positive number because we're looking for the total area. And so that 49 sixths, once again, looking at our graph down here, that 49 sixths represents this area plus this area plus this area. And compare that to our previous answer, which was negative 5 sixths, which was the first area minus the second area plus the third area. And so that concludes this introduction to the fundamental theorem and how to use it.